Hi, grade nines. So today we are going to talk about concentration and toxicity and how that relates to impacts our environment and even how it connects to acids and bases from the last concept that you learned. So saying that, looking at your learning outcome is that you're going to learn units of measurements that allow for you to understand the different concentration of substances in the environment. And you're also going to learn how concentrations relate to toxicity. So, success criteria. How do you know you're going to be completely understanding these concepts? You can define concentration. You can identify the following acronyms. So, what does ppm, ppb, ppt stand for? And you can compare the levels of concentrations of different substances. Next, I can define acute and chronic toxicity. I can explain LD50 in relation to concentration levels of a toxin, and I can look at data and determine which toxins are more dangerous. So, if we're looking at what does actually concentration mean, okay? Concentration is often represented as a percentage, okay? So if you were to look at a container of yogurt, okay, it is going to have 1%. Even milk is going to have 1% or 2% or 3.25%. And that percentage is going to tell you how much fat content is in it. So it is representing its concentration of the amount of a substance. If it is 0%, it is supposed to have 0% concentration of fat in it, okay? So in a yogurt that says 1%, that means you're getting 99 grams of everything else and 1 gram, 1% of that fat, okay? So, unfortunately, percentage isn't always great for low concentrations, and that is what we end up dealing with in regards to chemicals that show up in our environment, like mercury and nitrates, and even percentage or concentration of carbon dioxide in the air. So we, instead of using percentage for concentrations, end up using, okay, 3 different units, essentially: ppm, ppb, and ppt. Okay, and they stand for, this is something that you want to put in your notes: parts per million, parts per billion, and parts per trillion. To get a feel and an idea of what that means in regards to how small it is, okay. Oh, please don't change on me. Nope, it did. Go back. Sorry, guys. If you were to think about an Olympic-sized swimming pool, okay, it has, probably not a random fact, 660,000 gallons of water in it. That is a lot of water, okay? Now, 1 part per million is like saying there's 1 1/4 2-liter bottles, so right there, of water in that massive amount of swimming pool. 1 parts per billion, so even less amount, is a half a teaspoon, okay? 2.5 milliliters in 660,000 gallons, okay? That is a very, 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 very tiny amount within a large amount. So, parts per million is the one that we see the most of. And it's used mostly in environmental chemistry. So what this means is you have 1 milligram in a liter of a substance. So to give you an idea of concentration, so if you were to look at this first container This has 0, it's just plain old normal water. In the next one, it has 1 part per million. Notice you can't see it, but there is actually a chemical within that substance. The next one is 10. You can't really still see a difference, 100 parts per million. Now, it's not until we get to see about 1,000 parts per million of the chemical within the substance that you start seeing it. So we end up, and we're going to talk about it, how we end up measuring it and kind of watching for things, because concentration isn't something that's necessarily visible in regards to how much can end up harming us. Okay? So this is just another visual for you. And come on. The lower one is 1 part per million. The second one, you can even see the color difference, 10 parts per million. As you go up in concentration, you increase, and you can see how much more intense that concentration actually is. So, what does this actually all mean, and how does it impact us? Concentration and that parts per million unit is used to measure things, for example, that are in our water. Okay? In Canada, they, at water treatment plants, will actually do measurements for toxic chemicals, or just the presence of chemicals, to make sure they are all in the appropriate level, safe for human consumption. Okay? So, for example, water is tested for aluminum, let's say arsenic, chromium, mercury, nitrate. It also be tested for fluoride. Some cities do have fluoride automatically in them. And all of those chemicals do have some toxic effects. So if that concentration is too high, we could have some health problems. So that is why we test our water, and they are looking for concentration levels, and they're looking for it in parts per million. So aluminum has a concentration kind of max at 0.2 parts per million. You notice it doesn't really seem like that much. That's because even though aluminum has no health effects, we still don't necessarily want it in our water. But as you can keep going, we know arsenic is kind of not a great thing. Arsenic can cause cancer. Notice it is a very small concentration that is allowed within our water. And mercury is another one. 0.001 parts per million is allowed in our water because it can cause some brain problems. It is very poisonous to us. So that one is constantly monitored. Okay. I said carbon dioxide is even something that is monitored at the Moana. It's an observatory in Hawaii. It was actually recording the carbon dioxide concentration. And you'll notice in 1960, it was quite low. And in 2010, it has obviously progressed upwards. And they actually measure the carbon dioxide concentration in parts per million. And to give you one more little visual, how much is 1 parts per million? So 1 part per million is 3 gallons in a 42-gallon barrel. 1 part per billion is 1 drop added to a large tanker truck. 1 parts per billion is 10 little tiny drops added to the Rose Bowl if it was to be filled with water. Obviously, it's not. And you rarely would see this one. I've never seen it, but 1 parts per quadrillion is 2 teaspoons added to the Great Salt Lake of Utah. Okay? So very tiny amounts. And when we're looking at that concentration measurement, it relates to toxicity. Okay? So toxicity is, this is an important piece, the ability of a chemical to harm an organism. So if something is extremely toxic, it can end up harming you. If you ingest it, or maybe you inhale it, or you're just exposed to it in the air and you touch it, but that exposure can harm you. Now, there's two different types of toxicity. Acute toxicity, it is not cute and cuddly. And then there's chronic. Okay? Both are not good. Both cause health problems. But acute is when symptoms occur after only one exposure. So if you are exposed to methanol, you'll actually see symptoms after one exposure of it right off the bat. But chronic toxicity, you might not necessarily see symptoms right away. You will have to be exposed to it possibly over a long period of time before symptoms end up showing up, because the chemical has to basically accumulate within your body in order to show representation of the presence of it. And an example of that would be lead. Okay, you can get lead poisoning, and it would be classified under chronic toxicity. So how do we measure toxicity? This is a new term for you, LD50. LD50, the name actually kind of implies what it means. LD stands for lethal dose. Okay, lethal means killing you. And 50 stands for 50% of the population. This does take into consideration the fact that some people will react quicker, or some people won't react at all to a chemical. That is all considered. Everybody does have different effects to different chemicals. We are not all clones of each other or identical to each other. So LD50, or lethal dose 50, is the amount of the substance, basically. How much does it require to kill off 50% of the population that it's exposing itself to? Okay? Usually this is tested with rats. It is not tested with humans right off the bat, because not many people were willing to volunteer themselves to check this one out. So if you look at something that's familiar to you, for some of you not so much, if you look at coffee, or if you look at nicotine, okay, nicotine in cigarettes has been tested for LD50. Almost all chemicals have been. It has an LD50 of 0.86 milligrams per kilogram. That means it takes that amount, okay, to kill 50% of the population that would be exposed to the chemical. Believe it or not, nicotine's more toxic than caffeine. Caffeine, yes, caffeine is a chemical, has an LD50 of 130 milligrams per kilogram. So you'll notice 130 is much larger than 0.86. So this is not a concentration comparison. This is the amount that it would take to kill 50%. This is the amount. So the caffeine takes a larger amount to kill 50% of the population. So the higher the number, the less toxic the chemical is. Caffeine is not that toxic, and you're going to say, can you actually consume enough caffeine for it to kill you? No, your body cannot actually ingest enough of it, and your body processes it too fast in order for it to kill you. So no, you cannot drink enough caffeine or espresso shots or energy drinks in order for that to be the sole factor of killing you in regards to the LD50 part. Okay, so don't worry about it, but you probably still shouldn't be drinking an excessive amount of caffeine. So, question and answer time. Toxic nicotine has an LD50 of 0.86, like I told you, milligrams per kilogram. For a test sample of 2,400 rats, how many would survive this dosage? Okay. LD50 is 50% of the population. Well, there's the population of rats. So they get that LD50 exposure, which means 2,400 divided by 2 is 1,200 rats would end up surviving this dosage. Okay. And then toxicity wise, which one's most dangerous? So we have 4 different chemicals there. No, you don't have to pronounce them. But if you were to see this on a chart, which one would be the worst one for you? Which one's going to be more on the safer side? Still not great. Okay. I said the higher the number, the less toxic it is. So chloridane is the least toxic, and dioxin is the most. So this is the most dangerous. And then our next one is that guy. And then we're dealing with solanine. So least to most, based strictly on numbers. The higher the number, the less toxic it is in regards to LD50 measurements. Okay, believe it or not, this comes into play constantly. Sometimes chemicals can't always be tested before they're used, especially with drug or substance approval in order to solve maybe some medical issues. Okay, and this is a constant debate on whether all the testing should be able to go through before humans can use it, or you could allow human exposure and testing of it before everything is all good to go. And this is just something to think about. Do you actually agree with it or not? Most people would say right off the bat, their instinct is, oh no, it's not safe for humans. I'm not going to let them. Why would you test it on a human if it's not safe for humans and you don't know yet? Well, some people do have medical issues that there is no cure for or no known assistance for. So some people are actually willing to say, if I could possibly improve my lifestyle because I'm dying or I'm extremely ill, they might consider that. And so this is actually things that are debated. Governments and legislative bodies are constantly pressured to relax the strict testing we have on substances by doing things like measuring their toxicity and how much concentration can actually impact us. So just a thing to think about. Usually we have a large discussion about this, but we're not going to do that today. Okay. And the one thing that we do need to think about when we're talking about that issue is just the fact that, okay, risk to humans for a substance is difficult to determine. You can't just say, oh, well, one person reacted that way, so therefore this person's going to react that way. It's difficult to determine because toxicity testing isn't usually done on humans. It's usually done on rats. Rats aren't the same as humans. Often you have this false assumption, right, that humans react the same as a lab mouse or a rat, or they might react the same as the next kind of animal that they are going to talk about. They have had more than one drug that was used on rats that was completely safe for rats, and it caused some major problems in humans, actually. There's one drug called thalidomide that was used about 40-ish years ago, and it ended up having some horrible after effects. Number 3, toxicity depends on exposure. Skin contact is usually less toxic than inhalation or ingestion. So eating something versus just touching it can be a different type of symptom and how kind of powerful it ends up being for a person. And the last one is that every individual reacts differently to chemicals. Okay, we don't know how, we can't say it's a blanket for all humans. And that is it for toxicity and concentration. So we have, okay, what is concentration? We have acute and chronic toxicity. We have parts per million, parts per billion, and parts per trillion. And then we also have LD50. That is it. That is all. I hope you guys have a good rest of your day. Bye.